Hello students, here in this lecture we'll discuss the idea of Coriolis force. Okay. So before discussing the idea of Coriolis force, let me tell you something more fundamental. We know that force, if I'm talking of translational motion, that is motion in a straight line, then we define force as rate of change of momentum, dp by dt. What does this expression mean? This expression tells you that whenever there is a change in momentum, it means there must be a force who is behind all this scene. It means this force must have caused the change in momentum. Analogously, in circular motion, we have this idea of torque and angular momentum. It says that torque tau is equals to rate of change of angular momentum. Now physically, what does it mean? It means that if an object is moving in circular motion, and if during the motion in circular path there is any change in angular momentum, then this change in angular momentum is brought by a particular torque. Okay, now we know that torque is also written in terms of force, which is F dot R. F is a linear force. Okay, now we know that linear forces, they cause rotation. If you look at the circular table, if I apply a linear force along this direction, then obviously this circular table is going to move in circles in anticlockwise direction. Okay, anyways, now consider this this circular table is moving around about this point O. O is the center of the table with angular velocity omega. Okay, if there is a boy sitting at this particular point, say the boy is sitting at point P, can you tell me what at point P, what is the angular momentum? We know that angular momentum, we know this expression from circular motion. Angular momentum is given by m omega r square. Okay, how do we know this? Let me remind you that angular momentum is actually m into v t r. Now why I wrote vt? Vt is the tangential velocity of point P when it is moving around circles. So when the point P reaches here, the tangential velocity is along this direction. When the point P reaches here, as it is moving in circle, the tangential velocity is in this direction. So if you multiply this tangential velocity Vt into r, r is the distance of the point P from the origin, so this is r. So if you multiply the mass Vt into r, you get what? You get angular momentum. But what is Vt? We know that linear velocity can be written in terms of angular velocity as v is equals to omega r. You know this from our circular motion chapter. So this gives us m omega r square. Okay, now tell me what happens when on this circular moving table point P starts running in the radial direction and reaches point P dash. If you look at point P dash, then at point P dash the value of angular momentum has changed. Now the angular momentum is m omega r dash square, where you can clearly see that r dash is less than r. It means when the point P, or when the boy at point P starts moving towards O, at point P dash its angular momentum has decreased. Or I can say in this way, when on a circular moving table a person starts moving from the edge along the radius towards the center, then the angular momentum goes on decreasing. And intuition says if there is any change in angular momentum, then this change in angular momentum is caused by some torque. So let's mathematically evaluate. Now d by dt of which angular momentum is changing? The angular momentum that is changing is m omega r square. Now since m is constant, omega is constant, derivative acts on r square, and we get 2m omega r into dr by dt. This is quite clear. Okay. This can be written in this way. Bring 2m omega. Now what is dr by dt? Dr by dt is the radial velocity Vr, the velocity with which the boy starts running towards the center, into r. If we equate this with F dot r, then this force looks very different. It looks weird. Look at the expression of this force. The expression of this force is F equals 2m omega v of r. Let me remind you, this is not centrifugal force, because the expression for centrifugal force was m v square by r, and this force acted radially inward or outward. If it is centripetal, then it acts inward, and if it's centrifugal, it acts outward. If you look at this particular force, it looks entirely different from the expression of centripetal force. This force is called as the Coriolis force. Okay. Now question is, in which direction is this force acting, and does it has another origin? We'll look at in the next lecture.